Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 23, 2025, just yesterday. The big move is switching from pixel-aligned to voxel-aligned Gaussians, and it delivers state-of-the-art results. For example, PSNR 31.30, SSIM 0.941, and LPIPS 0.075 on Real Estate 10K. The paper is titled, Voxel-Splat, Rethinking Feed-Forward 3D Gaussian Splatting with Voxel-Aligned Prediction. And, as we will see later, the gains are both cleaner and more consistent. In short, the method improves geometric consistency, adapts Gaussian density to scene complexity, and scales robustly across datasets. Also, the authors shared their GitHub. You will find a clear README summarizing VolSplat, a method overview and pipeline, current todos to release code and model checkpoints, citation details, and contact information. The repository uses an MIT license, credits DepSplat, and for now mainly offers documentation while the implementation is prepared. On Hugging Face, you'll find the VolSplat model card outlining voxel-aligned 3D Gaussian splatting. No downloadable weights or parameter sizes yet, and no usage examples provided. Figure 1 contrasts two pipelines that predict Gaussians for novel view synthesis. Gaussian splatting means representing a scene with many soft ellipsoids that render into an image, which is fast and expressive. The top panel contrasts pixel-aligned prediction, which ties each pixel to a Gaussian so errors from matching propagate across views. The bottom panel shows voxel-aligned prediction, which fuses evidence in a 3D grid so geometry stays consistent and density adapts to scene complexity. The message is that aligning in 3D resolves view bias and occlusion issues. Well, Figure 2 shows the full volume splat pipeline, which converts multi-view images into voxel-aligned Gaussians for fast, novel view rendering. The left column holds input images that feed a multi-view feature extractor. A depth module builds plane sweep cost volumes, meaning it compares views across many candidate depths to infer per view depth, so features can be unprojected into a 3D voxel grid. A sparse 3D decoder refines voxel features, and the right side predicts Gaussians for rendering. So Figure 4 compares visual results side by side, which means a qualitative comparison that shows how outputs look rather than just scores. The left block covers Real Estate 10K, and the right block shows ScanNet. Across the red highlighted areas, VolSplat renders sharper edges and fewer floaters, so geometry stays consistent. Inputs and baselines blur stair rails, chair legs, and doorway boundaries, while VolSplat matches the ground truth more closely. So, while Figure 4 highlighted cleaner visuals, Table 3 shows cross-dataset generalization in a zero-shot transfer test, which means the model is evaluated on a new dataset without fine-tuning. Trained on Real Estate 10K and tested on ACID, VolSplat reaches PSNR 32.65. It also records SSIM 0.932, which signals strong structural fidelity. LPIPS falls to 0.092, so perceptual errors look lower. Baselines cluster near PSNR 28, indicating a sizable margin. The method uses roughly 65,000 primitives, which is comparable to competitors yet delivers better quality. Alright, Table I reports performance on Real Estate 10K and shows a clear lead for VolSplat. PSNR rises to 31.3, which signals less pixel error than all pixel-aligned baselines. SSIM climbs higher as well, indicating stronger structural fidelity. LPIPS drops, a learned perceptual metric that tracks visual closeness. PGS denotes average per view Gaussians, and counts stay comparable. Alright, two takeaways stand out. Switching from pixel-aligned to voxel-aligned Gaussians fixes view bias and occlusion issues, and the adaptive density plus sparse 3D decoder deliver consistent geometry with state-of-the-art quality and strong transfer. The broader implication is a scalable, feed-forward 3D reconstruction path for fast deployment. Thanks for listening. I'm Alex.